Hi, I'm Deniz, and I will be talking about my graduation project. Actually, a technique I've used in my graduation project, which is a very powerful technique. It's called dream. So, once upon a time, I had a dream. There was a girl named. Just joking. It actually stands for Diffusion, Rectification, and Estimation Adaptive Models. So, why I used it? So, there are two main reasons behind it. The first one, it significantly improves the fidelity by letting the model to learn from its own mistakes. The second one, it leads much faster convergence. Before I get into Dream, let me recap the foundational LDM intuition. Okay, so we apply noise to an image, which is x0. It's denoted as x0, and we put a noise onto it, which is sampled from standard normal distribution. And our model's task is basically to predict the noise that was added onto x0. But please be aware of the difference. We are not predicting the image itself. It's an approach as well, by the way. Some people implement LDMs just like that. However, in this case, we are just predicting the noise. As I mentioned, we are not predicting the image itself. We are predicting the noise. Also, we call it epsilon. Normally, this is a direct prediction. But Dream says, wait, we know ground truth, we know the predicted noise. So ground truth is also a noise, Gaussian noise. So by subtracting them, we can get a difference vector. This represents the deviation from the ground truth. So basically, in a manner of speaking, the error the model made. Then we multiply this deviation vector by a specific coefficient and add it back to the ground truth noise. So we had a difference vector, deviation factor, and the ground truth noise. So we add that onto that ground truth and then pass it to the model again. And this forces UNIT to focus specifically on the pixels where it struggled to denoise mostly. So it's like a teacher that highlights the exact mistakes in a student's homework. By the way, the coefficient I mentioned is square root of beta power of p. So we use p to control the intensity of dream or rectification. So if it's too low, we may get overly smooth images, lack of sufficient details. If p is too high, we stay too close to the original noisy path. So it's all about finding that sweet spot for faster convergence and fidelity. So in my case, I've used 10 as a value of p because my project was about virtual try-on, which you should transfer a garment onto a person. So we should conserve the textures and wrinkles of the clothes accurately. In Dream paper, they suggest that the value of 1 is the best one in their experiments. I tried 1 as well, but I got overly smooth images. It didn't satisfy my expectations. And another thing I can say is LDM basically use UNet backbone, and generally with self-attention and cross-attention layers. Although the training process is made up with one step, xt to x0, t picks randomly between 0 and 1000. The inference is a multi-step operation. So another thing that paper tells us is two-pass training methodology is highly beneficial for inference time compatibility with the training, because training is a one-step operation. We just pass a noised image and our model tries to denoise that image in just one step. However, in inference time, it's completely different. I hope that will be helpful in your study. If there are any flaws or mistakes in my demonstration, please let me know. Thank you so much. Peace out.